Video about ANOVA and MANOVA. In this video we will talk about in further. Let's first we talk about the multivariate procedure for assessing the group differences. As statistical interface procedure, both the univariate technique t-test and ANOVA and their multivariate extension hotlines T2 and MANOVA are used to assess the statistical significance of differences between groups. In the t-test and ANOVA, the null hypothesis, the equally chanced of the difference between group, that is the t-test and ANOVA, equally of a single dependent variable means across the group. In the multivariate technique, the null hypothesis tested in the equality of vectors of means on multiple dependent variables across the group. The distinctions between the hypothesis test in ANOVA and MANOVA is illustrated in figure 1. In the univariate cases of single dependent measurement is tested for equality across the group. In the multivariate cases, a variate is tested for equality. The concept of variate is instrumental is discussion of many multivariate techniques. In MANOVA, the researcher actually has two variates, one for the dependent variable and another for the independent variable. The dependent variable is of more interested because the metric dependent measurement can be combined in a linear combination, as we have already seen in multiple regression and discriminant analysis. Those unique aspect of MANOVAs in the variate optimally combine the multiple dependent measures into a single value that maximize the difference across the group. Here is the table 1 about the ANOVA, the null hypothesis. All group means are equal to T from the same population. Null hypothesis testing of ANOVA and MANOVA. Let's talk about the two group cases. Hotlines T2 assume the test researcher were interested in both the appealing and purchases intent generated by two advertising message. If only univariate analysis were used, the researcher would perform separately. T-test won the rating of both the appeal of the message and the purchases intent generated by the message, yet the two measures are interrelated. Those what is the really desire is a t-test of the differences between the message on both variable collectively. Here is which hotlines T2, a specialized form of MANOVA and direct extension of the univariate t-test, can be used. Controlling for type 1 error rate. Hotline T2 provide a statistical test of the variate from the dependent variables which produce the greatest group differences. It is address the problem of inflating the type 1 error rate that arise when the making a series f t-test group means on several dependent measurement. It control this inflation of the type 1 error rate by providing a single overall test of group differences across all dependent variable aspect fixed alpha level. How does hotline T2 achieve these goals? Consider the following equation for a variate of dependent variable. C is equal to W1 and X1 is equal to plus W2 X2 plus number of Wn n Xn. C, what is the C? C is a composite or variate score for a respondent. Wi wait for the dependent variable. X1 is dependent variable. In our example, the rating of message appeal combined with the purchase intention from the composite. For any set of weight, we could compute composite score for each respondent and then calculate an ordinary t statistic for the difference between group on the composite score. However, if we can find a set of weight that gives the maximum value for t statistic for the set of data, these weight would be the same as the discriminant function between the two groups. The maximum statistic that result from the composite score produced by the discriminant functions can be squared to produce the value of hotline t square. The The computation formula for hotline T2 represent the result of mathematical derivations used to solve for a maximum t statistic and implicitly the most discriminating linear combination of the dependent variable. It is equivalent to saying that if we can find a discriminant factor functions for the group that product a significant to T2, the two groups are considered different across the mean vectors. Statistical testing. How does hotline T2 provide a test of the hypothesis of the group differences of the vector or mean square, just as the t-test following a known distribution under the null hypothesis of no treatment effect on the single dependent variable. Hotline T2 follows a known distribution under the null hypothesis of no treatment effect on any of the set of dependent measures. This distribution turned out to be an F distribution with P and 1 and 2 is equal minus 2 and minus 1 degree of freedom after the adjustment where P the number of dependent variables. To get the critical value for hotline T square, we find the table value for F as a specified alpha and compute T2 crite as the following. T2 crite is equal to P uh, under bracket n1 plus n2 minus n. This is the formula of T2 crite. The key group case MANOVA. Just as ANOVA was an extension of the t-test, MANOVA can be considered an extension of hotline T2 procedure. We devise dependent variable way to pursue a variable score for each respondent that is maximally different across all of the group. Many of the same analysis design discussed for ANOVA apply to MANOVA, but the method of statistical testing differs markedly from that ANOVA. Analysis design. All of the issues of analysis design applicable to ANOVA, number of level per factor, number of factor, etc., also apply to MANOVA. Moreover, the number of dependent variable and the relationship among these dependent measures raise additional issues that will be discussed later. MANOVA enable the researcher to assess the impact of multiple independent variables on not only the individual dependent variable but on the dependent variable collectively as well. Statistical testing. In the case of two groups, when the variate is formed, the procedure of ANOVA are basically used to identify whether the differences exist with three or more groups, either by having the single dependent variable with the three level or by using the two and more independent variable. The analysis of group differences become more closely allied to discriminant analysis. For three and more groups, just as in discriminant analysis, multiple variates of the dependent measurement are formed. The first variate trimmed a discriminant function specify a set of the maximize the differences between the group, thereby maximizing the f value. The maximum f value itself enable us to compute directly what is called Rowe's greatest characteristic root statistic, which allow for the statistical test of the first discriminant function. The greatest characteristic root statistic can be calculated as Rowe's GCR k minus 1. This is the formula while testing the statistical. To obtain a single test of the hypothesis of no group differences on the first vector of mean score, we could refer to table of Rowe's GCR distribution, just the F statistic following a known distribution under the null hypothesis of equivalent group. A single dependent variable, the GCR statistic following a known distribution under the null hypothesis of equivalent group means vector, that is the group means are equivalent on the set of dependent measures. A comparison of observed GCR to Rowe's GCR given us a bias for rejecting the overall null hypothesis or equivalent group means vectors. Any subsequent discriminant functions are orthogonal. They maximize the differences among the group based on the remaining variance not explained by the prior functions. Those in many instances, the test for differences between group involves not just the first variate score but also the set of variate score that are evaluated simultaneously. In this case, a set of multivariate tests available, that is the Wilks, Lambda, Pillai criterion, each base situated to specify situation of testing these multiple variates. Difference between MANOVA and discriminant analysis. We noted earlier that is a statistical test. MANOVA employed a discriminant function which is the variate of dependent variable. The maximum, the difference between group. The question may arise, what is the differences between MANOVA and discriminant analysis? In some aspect, MANOVA and discriminant analysis are mirror image. The dependent variable in MANOVA, a set of matrix variables are the independent variable in discriminant analysis, and the single non-metric dependent variable of discriminant analysis become the independent variable in MANOVA. Moreover, both use the same method in forming the variates and assessing the statistical significance between groups. The differences, however, center around the objective of the analysis and the role of the non-metric variables. Discriminant analysis employs a single non-metric variable as the dependent variable. The categories of the dependent variable are assumed as given and the independent variable are used for from variate. The maximally difference between the group formed by the dependent variable categories. MANOVA used to set of matrix variable as dependent variable, and the objective become finding group of respondents that exhibit differences on the set of dependent variables. The group of respondents are not specified. Instead, the researcher used one and more dependent variable, non-metric variable, to form groups. MANOVA, even while performing these groups, still retains the ability to assess the impact of each non-metric variable separately. Let's talk about a hypothetical illustration of MANOVA. A simple example can illustrate the benefit of using MANOVA while also illustrating the use of two dependent variable to assess difference on two dependent variable. Assume that HBATS advertising agency identified two characteristics of Harvard's advertisement: product type of being advertised and consumer status, which they through caused differences in how people evaluate the advertisement. They asked the research department to develop and execute a study to assess the impact of these characteristics on advertising evaluation. Analyzing design. In designing the study, the researcher team defined the following element relating to factor: use the dependent variable and sample size. Factor factors Two factors were defined representing product type and customer status. For each factor, two levels were also defined: product type P product 1 versus product 2, and customer status current customer versus ex customer 1. Combining these two variables, we get four distinct group. Here is a customer's current customer and ex customer: product 1, product 2, group 1, group 2, group 3, group 4. Dependent variable. Evaluation of the HBAT advertisement using two variable: ability to gain attention and persuasiveness, measured with a 10-point scale. Sample respondent shows advertisement and asked to rate them and the following dependent measurement. Here is the hypothetical example of MANOVA: product 1, product 2, X customers ID 1, 2, 3, 4, attention purchases, total ID attention purchases, and total Value are represented as on the 10-point scale, 1 low and 10 high. Difference from discriminant analysis. Although MANOVA construct the variate and analysis differences in a manner of similar to discriminant analysis, the two technique different market marked in how the group and form and analyzing. Let us use the following example to illustrate these differences. With discriminant analysis, we could only examine the differences between the set of four groups without distraction as to a group characteristic, product type of customer status. The researcher would be able to determine whether the variate significantly differed only the across the group but only not assess which characteristics of the group related to see differences with MANOVA. However, the researcher analyzes the differences in the group, also assessing whether the differences are due to product type, customer type, and both those. MANOVA focusing the analysis of the composite of the group based on the characteristic in the independent variable. MANOVA enable the researcher to propose a more complex research design by using any number of independent non-metric variable within the limits for from the group and then look for the significant differences in the dependent variable variate associated with specified non-metric variables, forming the variate and assessing differences. With MANOVA, we can combine multiple dependent measures into a single variate that will be the assumed for differences across one or more independent variate. Let us see how the variate is formed and used in our example. Assume for this example that the two dependent measurement, attention and purchases were equally weighted when assumed into the variate value. Variate total score. This first step is identical discriminant analysis and provide a single composite value with the variable weighted to achieve maximum differences among the group. With the variate form, we can now calculate means for each of the four groups as well as the overall means for each level. From table 1 can seen several patterns. The four group means for the composite variable total, that is for 4.25, 8.25 and 11.27 and 11.0 vary significantly between the group, being quite differently from each other. If we were to use discriminant analysis with these four groups specified and the dependent measurement, it would be determined the significant differences appeared on the composite variable and also the both dependent variable. Attention and purchases did not contribute to the differences. Yet, in the doing so, we would still have no insight into how the two dependent variables contributed to these differences. MANOVA, however, goes beyond analyze only the differences across the group by assessing the whether the product typically or the customer status created group with these differences. The discrimination is accomplished by evaluating the category means denoted by the symbol, which are shown in the figure 2. Along with the individual group means, the two line contact the group X customers and customer for product 1 and product 2. If we took a product type ignoring the distinctions as the customer status, we can see a mean value of 8.0 for user of product 1 versus a mean value of 1.125 for user of product 2. Likewise, for customer status, X customer had a mean value of 6.25 and customer a mean value of 12.875. Visual examination suggests that both category means show significantly differences, with the differences for the customer type 12.875 minus 6.25 is equal to 6.625 greater than the product 11.125 is minus 1.0 is equal to 3.125. MANOVA and GLM, this is the table, graphical display and the group means of variate for hypothetical example. By being able to represent these independent variable. Category means is the analyze the MANOVA analysis not only shown the overall differences between the four groups to occur as with discriminant analysis, but also the both customer type and product type contribute significantly to forming these differing groups. Therefore, both characteristic cases significant differences are finding not possible with discriminant analysis. A decision process for MANOVA. The purpose of performing a multivariate analysis or variance is similar to that found in many other multivariate techniques. So it can be described through a 6 stages model building process. The process being with the significant specification of the research objective, then proceed to number of design issues, finding a multivariate analysis, and then issues address. The process continue with estimation of the MANOVA model and the assessment of the overall model fit. When an acceptable MANOVA model is found, then the result can be interpreted in more detail. The final step involve efforts to validate the result to ensure generalizability to the population. Figure 3 stage 1 minus 2 and figure 4 stage 4 minus 6 shows the later in the text. Provide a graphical portrait of the process with the discussion in the detail in the following section. MANOVA and GLM research problem. There is the stages of research. Number 1, research problem. Specify type of the research problem. Multiple univariates, structural multivariates, intrinsically multivariate, selection of dependent variable. Stage 2, research design issue. Advocate sample size per group, use of covariate, selecting the treatment independent variable, number of independent variable, 1 simple MANOVA, 2 or more, developing the factor analysis interpretation. This is the stage 3. Interactions as assumptions: independence, homogeneity of variance, covariance matrix, normality, linearity, multilinearity of dependent variables, sensitivity, outlier. To stage 4. These are the stage 1 to 3 in the multivariate analysis of variance. MANOVA's decision diagram. Stage 1 objective of MANOVA. The selection of MANOVA is based on the desire to analyze a dependent relationship represented the differences in a set of dependent measurement across a series of groups formed by one or more categorical independent measures. As such, MANOVA represent a powerful analytical tool suitable to a wide array of research questions, whether used in the actual quite experimental situation, field sitting or survey research for which the independent measurement are categorical. MANOVA can provide insight into not only the nature and productive power of the independent measurement but also the intercorrelationship and the differences seen in the set of dependent measures. When should we use MANOVA? With the ability to examine the several dependent measurements simultaneously, the researcher can gain in the several ways from the use of MANOVA. Here we discuss the use in MANOVA from the perspective of controlling statistical accuracy and efficiency while still providing the appropriate form for testing multivariate question. Control of experiment meant wide error rate. Those use of separate univariate ANOVA or t-test can create a problem when trying to control the experimental wide error rate. For example, assume that we evaluate a series of 5 dependent variables by separate ANOVA, each time using the point 0.5 as the significance level. Given no real differences in the dependent variable, we would expect to observe a significant effect on any given independent variable 5% of the time. However, across our 5 separate tests, the probability of the type 1 error lies somewhere between 5% if all dependent variables are perfectly correlated and 23% 1 minus 0.95 underscore 5. If all dependent variables are uncorrelated, those a series of separate statistical tests leave us without counter of our effective overall or experiment wide type 1 error rate. If the researcher desire to maintain control over the experimental wide error rate and at least some degree of correlation is pre-test among the dependent variable, the MANOVA is appropriate. Let's talk about the differences among the combination of dependent variable. A series of univariates, ANOVA test also ignore the possibility that some composite, a near combination of the dependent and variable, may provide evidence of an overall group differences that may go undetected by examining each dependent variable separately. Individual tests ignore the calculation among the dependent variable and in the presence of collinearity among the dependent variable. MANOVA will more powerful than the separate multivariate test in several ways. MANOVA many detect combined difference not found in the multivariate test. If multivariates are formed, then they may provide dimension of differences that can distinguish among the group better than single variable. If the number of dependent variable is kept relatively low, 5 or fewer, the statistical power of the MANOVA test equal to exceeded that obtained with the single ANOVA. The consideration, innovation, sample size, number of dependent variable and statistical power are discussed in the subsequent section. Let's we talk about type of multivariate questions suitable for MANOVA. The advantage of MANOVA versus a series of univariate ANOVA extended past the statistical issues in its ability to provide a single method of testing a wide range of different multivariate questions. Throughout the text, we emphasize the interdependent nature of multivariate analysis. MANOVA has the flexibility to enable the researcher to select the test statistical most appropriate for the equation of concern. Hand and Taylor have classified multivariate problems into three categories, each of which employs different aspects of MANOVA. In its resolution, these three categories are multiple univariate structure, multivariates, and intrinsically multivariate question. Multiple univariate questions. A researcher studying multiple univariate questions identify a number of separate dependent variables, that is age, income, education of customers, that are to be analyzed separately but need some control over the experimental wide error rate. In this instance, MANOVA is used to assess whether an overall differences is found between the group and then the separate univariate tests are employed to address the individual issues for each dependent variable. Structure multivariate questions. A researcher dealing with structure multivariate questions graded two or more dependent measures that have specified relationship among them. A common situation in the category is repeated measure where the multiple responses are gathered from each subject, perhaps over the time or in the pre-test post-test exposure to some stimulus such as an advertisement. Here MANOVA provide a structural method for specifying comparison of group differences on a set of dependent measurement while maintaining statistical efficiency. Let's talk about the intrinsically multivariate technique. An intrinsically multivariate questions involve a set of dependent measurement in which the principal concern is how they different as the whole across the group. Differences on individual dependent measurement are or less interested than their collection effect. One example is the testing of multiple measurement of responses that should be consistent, such as attitude, preference, and intention to purchase, all of which related to differing advertisement. The full power of MANOVA is utilized in this case by assessing not only the overall differences but also the differences among the combination of dependent measurement that would not otherwise to be appealed. This type of question is several well by MANOVA's ability to detect multivariate differences even when no single multivariate test shows differences, selecting the dependent measurement. In identifying the question of appropriate for MANOVA, it is important as so discuss the development of research questions, basically the selection of dependent measurement. A common problem encountered with MANOVA is the tendency of the researchers to misuse one of its strengths, the ability to handle multiple dependent measurement by including variable without the sound exceptual or theoretical basis. The problem occurred when the result indicate that subset of the dependent variable has the ability to influence interpretation of the overall differences among group. If some of the dependent measurement with the strong differences are not really appropriate for the researcher questions, then false differences may lead the researcher to draw incorrect conclusion about the set of whole. Those we are armature should always thus synchronize the dependent measurement and form of solid rotational for including them any ordering of the variables such as possible sequential effect should also be noted. MANOVA provide a special test step-down analysis to assess the statistical differences in a sequential manner, such as like the addition of the variable to the regression analysis. In summary, the researcher should assess all the aspects of the research question carefully and ensure that MANOVA is applied in the correct and the most powerful way. The following section addresses many issues that impact on the validity and accuracy of MANOVA. However, it is ultimate the responsibility of the researcher to employ the technique properly. Let's talk about the thumb rule one. We can call it the short summary of whatever we read. Now we will discuss decision process of MANOVA. MANOVA is an extension of ANOVA that examines the effect of one of no or more non-metric independent variable and two or metric dependent variable. In addition to the ability to analyze multiple dependent variable, MANOVA also the advantage of controlling the experimental wide error rate when some degree of intercorrelation among the dependent variable represent, providing more statistical power. The ANOVA when the number of dependent variable is 5 or fewer. Non-metric dependent variable create a group between which the dependent variable are compared. Many times the group represent experimental variable or treatment effect. Researchers should include only the dependent variable have strong theoretical support. Stage 2. Issues in the research design of MANOVA. MANOVA follow all of the basic design principle of ANOVA. Yet, in some instances, the multivariate nature of the dependent measurement require a unique perspective. In the following section, we will review the basic design principle and illustrate those unique issues arising in MANOVA analysis. Number 1, sample size requirement overall and by group. MANOVA, like all of other multivariate technique, can be marked effectively by the sample size used. What differs most for MANOVA and the other technique assessing group differences such as t-test and ANOVA is that the sample size requirement related to the individual group size and not the total sample paper. A number of basic issues arise concerning the sample size needed in MANOVA. As a bare minimum, the sample size each cell must be greater than number of the dependent variable. Although this concern may seem minor, the inclusion of just a small number of dependent variable from 5 to 10 in an analysis place and sometimes both some constraint on data collection. The problem is particularly in the field of experimentation on survey research where the researcher has less control the achieved sample. As a practical guide, a recommended minimum cell size is 20 observation. Again, remember the quality is per group, necessitating fairly large overall sample even for fairly sample analysis. In our earlier example of advertising message, we had only two factors, each with two levels, but this analysis would require 80 OBS deviation for an adequate analysis. As the number of dependent variable increase, the sample size required to maintain statistical power increase as well. We might defer our discussion of sample size and power un- unitile a later section, but as an example, required sample size increased by almost 50% as the number of dependent variable goes from 2 just 6. Researchers should strive to maintain equal or approximately equal sample size per group. Although computer program easily accommodate unequal group size, the objective is to ensure that an inadequate sample size is available for all groups. In most instances, the effectiveness of the analysis is directed by the smallest group, since those always making the sample size consideration a primary concern. Factorial design two and more treatments. Many times the researcher wishes to examine the effect of several independent variables or treatments, then using only a single treatment in either the ANOVA or MANOVA test. This ability to primary distinction between the MANOVA and discriminant analysis is being able to be determined the impact of multiple independent variables, informing the group with significantly group differences. An analysis with two and more treatments factors is called a factorial design. In the journal, a design with treatment is called an way factorial design. Selecting treatments. The most common use of factorial design involve those research questions that relate two or more non-metric independent variable to set a dependent variable. In this instance, the independent variable are specified in design of the experiment or included in the design of the field experiment or survey questionnaire. Type of treatment. As discussed throughout the chapter, a treatment a factor is a non-metric independent variable with the defined number of level categories. Each level represents a difference condition or characteristic that affect the dependent variable. In an experiment, these treatment and level are designed by the researcher and administered in the course of the experiment in field or survey research. They are characterized of the respondent gathered by research and the include in the analysis. But in some instances, treatment are needed in addition to those in the original analysis design. The most common use of additional treatments is to control for a characteristic that affect the dependent variable but is not part of the study design. In this instance, the researcher is aware of condition, that is method of data collection or characteristic of the respondent, for example geographic location, gender, etc., that potentially create differences in the dependent measurement even though they are not independent variable of interest to the study. Neglecting them, ignoring potential sources of differences, they are left unaccommodated for many obscure some result in interest to the study. The most direct way to account for such effect is through a blocking factor, which is a non-metric characteristic used post segment the respondent. The objective is to group the respondent to obtain greater within the group homogeneity and reduce the MSW sources of variety of. By doing so, the ability of statistical tests to identify differences in enhanced. Assume in our earlier advertisement example, we discovered that male in journal raise different than female to the advertisement. If gender is then used to be blocking factor, can evaluate the effect of the independent variable separately for male and female. Hopefully, this approach will make the effect more apparent than we assume they both similarity by not making the distractions on gender. The effect of message type of customer can now be evaluated for male and female separately, providing a more precise test for their individual effect. Those any non-metric characteristic can be incorporated directly into the analysis to account for its impact on the dependent measures. However, if the variable you wish to control for are metrics, they can be included as covariates, which are discussed in the next section. Let's talk about the number of statements. One of the advantage of multivariate technique is use of the multiple variable in a single analysis. For MANOVA, the feature related to the number of dependent variable that can be analyzed uh, cons- uh, concurrently, as already discussed. The number of dependent variable affect the sample size required and another issues, but what about the number of treatment, that is the dependence variable? ANOVA and MANOVA can analyze several treatments at the same time. Several considerations related to the number of treatments in the analysis. Number of cell form. Perhaps the most limiting issue involving multiple treatments involves the number of cell group form as discussed in our earlier example. The number of cell is the product of the number of level for each treatment. For example, if we had two treatments with two level of each and one treatment with four level of total of 16 cells, 2 into 2 into 4 is equal to 16 would be formed, maintaining a sufficient sample size for each cell. Assuming 20 respondent per cell would be the required total sample of 320. When applied to survey or field experimentation data, however, increasingly the number of cells becomes much more problematic, because field research is generally not able to administrate the survey individually to each cell of the design. The researcher must plan for large enough overall sample to find each cell to the required minimum. The proportion of the total sample each cell most likely to vary widely. That is, some cell would be much more likely to occur than others, especially as the number of cell increase. In such situation, the researcher must plan for an even larger sample size than the size determined by the multiple the number of cells by the minimum per cell. Let's look back to our earlier example to illustrate the problem. Assume that we have a sample two-factor design with two level of each factors, 2 into 2. If this is four cell design worth the control experiment, the researcher would be able to run assign 20 respondent per cell for overall sample size 80. What then if it is a field of survey? If it were equally likely that respondent would fall into each cell, then the researcher could get a total sample of 80 and each cell should have a sample of 20. Such tidy proportions and sample rarely happen. What if one cell was thought to represent only 10% of the population? If we use a total sample of 80, then this cell would be expected to have sample of only 8. Those if the researcher wanted to sample of 20 even for this small cell, the overall sample would have to be increased to 200. Unless sophisticated sampling plans are used to ensure that necessary sample per cell, increasingly the number of cells, those the likelihood of equal population proportion across the cell with necessity and even greater sample size than in a control experiment. Failure to do so would create situation in which the statistical proportion of the analysis would be marked dimension diminished, creating of interaction effect. Any Anytime more than one treatment is used, interaction affected are created. The interaction from represent to join affected of those or more treatment in a sample term. It means that differences between group of one treatment depends on the value of another treatment. Let us look at the sample example. Assume that we have two treatments designed, east versus west, and customer status, customers and non-customers. First, assume that on the dependent variable attitude towards the B Hbert customers scored 15 points higher than the non-customers. However, an interaction of the customer status would indicate that the amount of the difference between the customers two reasons. We might see that customer from the east scared 25 higher than non-customer in the east, while in the west the difference only 5 points. In both cases the customer scored higher, but the amount of the difference dependent on the reason. This outcome out an interaction of the two treatments. Interaction terms are created for each combination of treatment variable. Two ways interactions are variables taken two at time. There VR interaction are combination of three variables and so on. The number of treatments determine the number of interaction term possible. The following character shows the interaction rated for 2, 3 and 4 independent variable. This is the treatment A, B, A, B, C, A, B, C, D, two ways A into B, A into B, A into C, A into C, A into B, and three ways A into B into C. This is the three ways and four ways A, B, C, and D. We will discuss the various type of interaction term and their interpretation in their following section, but the researcher must be ready to interpret it and explain the interaction term whether the significant or not depending on the research question. Obviously, the sample size considerations are of the most important, but the researcher should not overlook the implication of interaction term. Beside using the latest on degree of freedom for each interaction, they present issues of interpretation discussed in stage 4. Let's talk about using covariates, ANOVA and MANOVA. We discussed earlier the use of blocking factors to control for influence on the dependent variable that are not part of the research design yet need to be accounted for in the analysis. It enables the researcher to control for non-metric variable, but what about metric variables? One approaches would be to convert the metric variable into a non-metric variable, that is median, split, etc. But this process is generally deemed unsatisfactory because much of the information contained in the matrix variable is lost in the covariance. A second approach is to be include the matrix variable as covariates. These variable can extract extraneous influences from the dependent variable, those increasingly the within the group variance. MSW, the process of following the step. Number 1, the procedures similar to linear regression are employed to remove variation in the dependent variable associated with one and more covariant. A conventional analysis is carried out on the adjusted dependent variable. In a simple statistical sense, it becomes an analysis of regression residual. One of the effects of covariate are removed. When used with ANOVA, the analysis is termed analysis of covariance. ANOVA, the sample extension of the principle of ANOVA to multivariate multi-dependent variable analysis is termed MANOVA. Objective of covariance analysis. The objective of the covariance is to estimate any effects that, number 1, affect only the proportion of the respondent, and second, vary among the respondents. Similar to use a blocking factor, covariance analysis can achieve two specified purpose: to eliminate some systematic error outside the control of the researcher that can be bias the result, two accounts to differences in the responses due to the unique characteristic of the respondents. In experimental setting, most systematic bias can be eliminated by the random assignment of respondent to various treatment. However, Non-experimental research such control are not possible. For example, in testing advertising, effect may different depending on the time of day or the composition of the audience and their reaction. Moreover, personal differences such as attitude or opinion may affect responses, but the analysis does not include them. As a treatment factor, the researcher used a covariate to take out any differences due to these factors before the effect of the experimenter are calculated. Let's talk about the selecting covariates. An effective covariates in one of the highly correlated with the dependent variable, but correlated with the independent variable. Let us examine why variance in the dependent variable from the bias of our error term. If the covariance is correlated within the dependent variable and not the independent variable, we can explain some of the variance with the covariance through the linear regression. Having a smaller residual unexplained variance in the dependent variance, this residual variance provides a smaller error terms MSW for the F statistical, and those a more efficient test of treatment's effect. The amount of explained by the uncorrelated covariance would not have been explained by the independent variable. Anyway, because the covariance is not correlated with the independent variable, thus the test of the independent variable is more sensitive and powerful. However, if the covariance is correlated with the dependent variable, then the covariance will explain some of the variance that could have been explained by the dependent variable and reduce its effect because the covariance is extracted first. Any variation associated with the covariance is not available for the independent variable. Thus, it is a critical that the researcher ensure that the correlation of the covariance and dependent variable is small enough such as the reduction is explanatory power from the reducing the variance that could have been explained by the dependent variable is less than the decrease in unplanned variance attributable to covariate. Number of covariates. A common question involves how many covariates to add it to the analysis. Although the researcher want to account for many extraction, extraneous effects, too possible too large number of will reduce the statistical efficiency of the procedure. A rule of thumb dictates that the maximum number of covariants is determined as following: maximum number of covariants, that is 0.10, sample size and number of groups, that is 1. For example, from a sample size 100 respondent and 5 group, the number of covariants should be the less than 6 and 6.10 into 10 minus 5 minus 1. However, the only two group that is analyzed could include to be 9 covariates. The researcher should always attempt to minimize the number of covariates while still ensuring that effective covariants are not eliminated, because in many cases, particularly with smaller sample size, they can markedly improve to sensitivity of the statistical test. Assumption for covariance analysis. Two requirements for used of an analysis of covariance and the following. Number 1, the covariance must have some correlation with the independent measurement. The covariance must have the homogeneity of the regression effect, meaning that the covariates then the equal effect on the dependent variable across the group. In the regression term, it implies equal coefficient for all groups. Statistical tests are available to assess whether this assumption should true, which covariate used. If either of these requirements that is not met, the use of covariate inappropriate. MANOVA counterparts of ANOVA design. Many types of ANOVA design exist and are discussed in the standard experimental design text. Every ANOVA design has its multivariate counterpart, that is, any ANOVA on a single dependent variable can be extended to MANOVA design. To illustrate that fact, we would have to discuss each ANOVA design in detail. Clearly, this type of discussion in the is not possible in the single chapter because neither book are developed to the subject of ANOVA design. For more information to read the refer the more statistical oriented text. In our next video, I call it ANOVA and MANOVA part 3 video. I will talk about a special case of MANOVA repeated measures.